Hi, welcome to Astrophysics podcast 4. In this one we're going to look at the pros and cons of reflectors, reflecting and refracting telescopes. Although of course you probably know in reality that almost all the large telescopes of the world are reflectors, and it's not really possible to construct a big refractor. We'll talk about that as we go along. So here's a mirror. In this case it's meant to be a section of what's called a spherical mirror. So this is just meant to be a section of a sphere, or that's meant to be an arc of a circle in 2 dimensions. And we're going to try and draw a ray diagram now to show spherical aberration. And we need to do that. We need 4 rays coming in, 2 kind of either side of the centre, and then we need to decide where the 2 inner rays are going to cross. So we need to draw the principal focus with putting arrows on, and again making sure that our reflections occur actually on the surface. It's very easy to make this ray diagram too complicated, and to have too many rays. 4 is, I think, really the only way of doing it. And the idea of the problem with this phenomenon called spherical aberration is that these outer rays will be brought to focus too close, not at the same point as the inner rays. And that's due to something called overcorrection. The curvature of the mirror is too great if the mirror is ground as a section of a sphere. So that's your spherical aberration diagram. Outer rays cross too far in, and the problem can be corrected by making the mirror a parabola. And of course all the world's big telescopes are reflecting telescopes. You've only got to grind one surface. If we quickly compare that to a lens, a lens needs 2 surfaces to be accurately shaped, which obviously in itself is more complicated. In reality, because of the chromatic aberration I'm about to show you, you actually need a minimum of 2 or even 3 lenses, which 4 or even 6 surfaces shape. But the final death knell of the refracting telescope with a lens is, because you can only hold the lens at the edge, obviously you can't have any structure, metal structure. You can't build a lens bigger than about 1 metre without the lens bending under its own weight. Whereas here we can have a giant steel structure around here. We can use light and strong materials to create 3-dimensional structures to support a mirror as large as you like. But anyway, this is a simple problem of what happens if you put light through a telescope. It's all based on the dispersion. Hopefully you've all seen with a lens, with a prism, the classic dark side of the moon look, that when you put light into a transparent material, the refractive index is different for different wavelengths, and as a result not all of our light emerges through one point. So the key thing here is to be able to construct differently what happens to the blue and the red light. And to be honest, the only reason I can do this from memory is because I now know the phrase red ahead. The red light, the longer wavelength light, is kind of dragged on less by the glass. The fact there are less waves seems to me that it's less affected, and so the rays are crossing further out from the lens. So the blue rays then, again, always choose a point for where your rays are going to go to before you drill them. Cross closer in. So what are the implications of this? Well, most of the light actually isn't red or blue. It's the greens and yellows in the centre of the spectrum, and those rays will be brought to a focus here. So the effect of looking at a star through a refracting telescope is that you see the star, and then you see this mixture of unfocused red and blue light either side, so you see a purple halo. Okay, I hope you found that helpful. Thank you.